So this is question 6 of this assignment. It turns out that this question is more of a classic exercise in many textbooks. They're not exercise questions. They're more like the problem questions, the more theoretical derivation style. So we had already seen this entity before. So where did we see that from? Well, we all remember that internal energy was a function of V and T. So we do remember we could, that's a U, right? dV plus U. Now, this thing, we called it internal pressure pi T dV. This one we know is called CV dt. So we've seen this before, and we already know that for an ideal gas, this quantity is equal to 0, if it's ideal. So delta U will always be equal to, N if you have moles, CV delta T. Classic equation. We also seen, we were simply given that this right here is also could be for any gas if we have an equation for it. Right? So if you have a real gas, you could say things like, okay, what if it's a virial, or what if it was a van der Waals gas? To calculate pi t, you simply need to take the derivative of p with respect to t, constant volume, put it right in here, multiply it by t, subtract off p, and you will solve for what pi t, for instance, for the van der Waals gas would equal. So I believe you've done this exercise already. But what this question's asking, show how this quantity, how do you get this from this? Now, the only way to do it, and this is a bit ahead of the chapter that you're in right now, so that's why I'll sort of walk you through it. You're going to have some Maxwell's relations coming in later in chapter 3. So, but like any math derivation, once you look up some things that are equivalent, you can do this. So what we'll do, first things first, to get here, someone would have to tell you that internal energy can be also described as a function of entropy and volume. So see how this time they're saying we'll get rid of T and we'll say let's watch the behavior of internal energy as a function of S and T. So what that means is we'll expand it out this way, right? So we're following the same math pattern. Okay. So now we're going to say, look, is there somewhere else in chapter 3 where we could look at an entity such as this one or that one? What could they be equal to so that it gets rid of this ugly entropy thing that's in it? So we'll find that in a minute. And then the other thing, we also know that we were asked to derive how this du dv was equal to this at constant t. So one of the things we want to do is we want to divide this by dv so we can start building du dv over here. So let's divide both sides by dv. So if we do that, we'll get ds dv, right? Because this term has to get divided by dv. This one will have it divided out. So now we're here. Well, now we would say to ourselves, if we're deriving this, why don't we say if t was held constant? Well, Do you see how if t was held constant, we could now turn this into that partial derivative notation? Because we've imposed it. So the short form of writing all this gobbledygook with that writing would be that. And what's interesting is this entity can often be viewed as a physical property of the gas. It's already been completely defined and set. So is this one. So these partial derivative notation parts, they're already set. When we instituted constant temperatures, do you see how this is a full derivative? This extra writing completely finishes defining these what look like a full derivative, which in effect turns them into what we would call a partial derivative. These ones are already there. So the way that the math relationships work out, you rewrite the partial derivatives as they were, but this one gets rewritten with the new constraint, constant temperature. Right? So now we're going to say to ourselves, okay, can we find something later in chapter 3 that gives us what these pieces are equivalent to? So we come to find out that Maxwell's relations and some others, that this happens to be equal to negative P. This part happens to be equal to, it's also proven to be equal to this. Right? And this one is equal to just T. So you can see how that becomes T times this gets replaced with that. And then that's plus this entity, which is negative P. So we've just done the derivation, how to get this equal to that. Right? So that's the derivation, which answers part 6a. So I believe that this is essentially 6a. So the next step, which I think you've already done, is show how an ideal gas, pi t is going to have to equal 0. And then for part 2, do the van der Waals. I think you've already previously done this. So you'd have to show using this, the derivation that coughs up an squared over v2. That's your answer. But you have to show how to get this. And that would answer question 6. And you've already done this one right here in chapter 2, and I believe even your Atkins textbook, some of your exercise questions essentially had you do this already. So you should be able to find that no problem.